Hello friends, welcome to this video session of thermodynamics of refrigeration and air conditioning subject. My name is Mr. S. V. Kumbar from Sharad Institute of Technology College of Engineering, Yadra, Ichalkaranji. Today we will start with the basics of thermodynamics. Already we have studied basics of thermodynamics in earlier videos, but there is a one separate point, thermodynamics of refrigeration, in our syllabus. So thermodynamics is the branch of physical science that deals with a relationship between heat and other forms of energy, generally mechanical, electrical or chemical energy, and by extension of the relationship between all forms of energy. So these are the few applications of thermodynamics. First application is power plant. In thermal power plant or in nuclear power plant, fuel is burnt. Generally in case of steam power plant, fuel is burnt with the help of which flue gases are produced. Those flue gases exchanges heat between water and hence water is converted into steam. So when this steam is expanded in the blades of steam turbine, heat energy is converted to mechanical energy first and mechanical energy is converted into electrical energy. Second application is shown, that is aircraft and spacecraft. In aircraft, gas turbines are used. In the gas turbine, here again there are three components: compressor, combustion chamber, turbine and nozzle. Here also heat energy is converted into mechanical energy is converted into electrical energy, and some part of flue gases it converts it into kinetic energy. That's why thrust is given to aircraft. Next, in internal combustion engine of car, we require fuel. When fuel is burnt, heat energy is converted into mechanical energy. In case of refrigeration system, here this is our area of interest. Heat energy is absorbed from an object which is to be cooled, and that heat energy is liberated to atmosphere. Solar hot water system, here also exchange of heat takes place and water is heated. In boats also there is a role of thermodynamics. Air conditioning, which is very similar to refrigeration system, it absorbs heat energy, moisture from air, and it is cooled. That cooled air is used for comfort purpose. Human body, that is the best example. The control of temperature of human body is governed with the help of laws of thermodynamics. So we'll study different forms of energies. So in this figure, mechanical energy, that is moving car. Mechanical energy is available at the crankshaft after combustion. Thermal energy, one example shown, that is melting of ice, heating soup. Electromagnetic energy, that is visible light, infrared radiation, radio waves, these are related to our day-to-day life. Electrical energy, lightning, power lines. Chemical energy, striking a match, food people eat, that is a chemical energy. Nuclear energy, nuclear fusion of sun and star, and nuclear fission inside the earth core. These are the different forms of energies. So few forms of energies are shown here, that is power plant, photovoltaic cell, then bridges, wind turbine, etc. Now coming back to modes of heat transfer. So there are three modes of heat transfer. First one is conduction. Generally conduction takes place in solids without any appreciable movement of molecule. This conduction is generally due to lattice vibration or free electrons. When heat energy is supplied at one end, if it is a metal, then transfer of heat energy takes place from one end to other end through displacement of free electron. So generally heat is transferred from one particle to another matter in an object without the movement of that molecule. Second one, convection. In convection, there is appreciable movement of molecule from one place to another place. And third one, radiation. Remember, radiation do not require any space or medium through which. First law of thermodynamics. Energy cannot be created nor it can be destroyed, but it can be transformed from one form to another form. That is the statement of first law. So in the second figure it is shown energy before is equal to energy after. So energy transformation or energy remain same even after energy transformation. This is nothing but first law of thermodynamics. So whatever amount of work is applied to the system, the heat which is liberated from the system can be calculated by the formula Q is equal to delta U plus W, or if we supply heat energy to a system, then this formula is written as delta U is equal to Q plus W. So if work is supplied to the system, it is considered as positive. If work is obtained from the system, then it is considered to be negative. Similarly, if heat is supplied to a system, it is considered as positive as it is endothermic reaction, and if heat is rejected from the system, then it is considered to be negative. So limitations of first law of thermodynamics, which is related to refrigeration also. Heat flows from a system of higher temperature to a system of lower temperature, and never from lower temperature to higher temperature. This is the direction of heat flow. If heat has to be flown from lower temperature to higher temperature, then external agency must be used. So heat is transferred from hotter side to colder side of the rod. One rod is shown here, but it will never flow from colder side to hotter side by itself. For that purpose, we have to use external agency. So from first law of thermodynamics, heat loss and heat gain must be equal in both process, but in fact it does not happen. Also, according to first law of thermodynamics, it is assumed that energy transfer can take place in either direction. It does not specify the direction of heat transfer. These are the some limitations of first law of first law of thermodynamics. So concept of heat pump and refrigerator. So in the first figure, a refrigerator is shown. Refrigerator is a device which extracts some amount of heat energy from a space to be cooled, and that heat energy is given to the warm environment. On the other hand, heat pump is a device which extracts heat from cold environment, and that heat is given to the warm houses, provided that the temperature of warm houses has to be maintained at a particular temperature which is greater than cold environment. So COP of refrigerant is given by desired output upon required input, that is cooling effect upon work input, QL upon W net. Similarly, COP of heat pump is equal to desired output upon required input. So desired output here is heating effect divided by work input, which is equal to QH upon W net. Both COP of refrigerator and COP of pump can be larger than 1, and there is a relation between COP of refrigerator and COP of heat pump as COP of heat pump is equal to COP of refrigerator plus 1. Second law of thermodynamics, which is related to refrigeration and air conditioning. So first law is Kelvin-Planck statement. So it is impossible to construct a machine which is working on a cyclic process which will work continuously without consuming any energy. So this is the statement of Kelvin-Planck. It means that any machine has to work continuously unless and until an input is given to that machine. For example, one reservoir is shown and one engine is shown. That engine will extract QH amount of heat and it will reject QL amount of heat to reservoir, so that it will run continuously. That is, heat engine is the best example. It works on Kelvin-Planck statement. Second statement is Clausius statement, and Clausius statement states that it is impossible to construct a machine which is working on a cyclic process which will reject heat from lower temperature reservoir to higher temperature reservoir without expenditure of work. So, few examples are shown under that Clausius statement. To run a refrigerator, we have to supply some initial work. So, refrigerator will extract QL amount of heat and it will reject QH amount of heat. For that purpose, work has to be supplied, W amount of work has to be supplied. Third law of thermodynamics. The entropy of a pure crystalline substance at absolute zero is zero. This is the statement of third law of thermodynamics. Now come to air refrigerator working on reverse Carnot with PV and TS diagram. We have already learnt Carnot cycle in internal combustion engine. So if its path is exactly reverse, that is from 1 to 2 isentropic compression, 2 to 3 isothermal compression, 3 to 4 isentropic expansion and 4 to 1 isothermal expansion. So it is nothing but Carnot cycle. Its path is exactly reverse, that's why it is known as reverse Carnot cycle. So in this type of refrigerator, a reverse Carnot cycle is considered. For a heat engine, the highest possible efficiency is achieved by the Carnot cycle. Similarly, in the refrigeration cycle, highest possible efficiency can be obtained when the system is working on reverse cycle. But there is not a single machine which is working on Carnot cycle, but it's a hypothetical cycle generally used for standard comparison. So these are the four processes involved in reverse Carnot cycle: isentropic compression, isothermal compression, isentropic expansion, isothermal expansion. So during isentropic compression process, air or refrigerant is compressed isentropically, and here pressure and temperature increases. The specific volume of refrigerant decreases. During isentropic compression, there is no heat exchange takes place from refrigerant to surrounding or vice versa. So this process is shown with the help of 1 to 2 curve or on TS diagram 1 to 2 line, that is isentropic compression. 2 to 3 isothermal compression. After isentropic compression, refrigerant is again compressed isothermally at constant temperature. The pressure increases while specific volume decreases. The heat is rejected during isothermal compression, and that rejected heat is given as Q rejected, that is Q2 to 3 is equal to T3 into bracket S2 minus S3. This process can be shown with the help of 2 to 3 curve on PV diagram and 2 to 3, that is horizontal line, that is isothermal curve on TS diagram. 3 to 4 isentropic expansion. The refrigerant is expanded isentropically and pressure decreases from P3 to P4. Specific volume increases from V3 to V4 as shown in PV diagram. The temperature also decreases. There is no heat transfer by this process. This process can be shown on PV diagram 3 to 4 or vertical line 3 to 4 on TS diagram. And last process is isothermal expansion process. The refrigerant expands at constant temperature, due to which the pressure of air decreases while the specific volume of refrigerant again increases. During this, the heat absorbed by air per kg of that refrigerant is equal to Q4 to 1 is equal to T4 into S1 minus S4, where S1 is the entropy at final stage, S4 is the entropy at initial stage, or which is equal to T1 into S2 minus S3. So this is all about thermodynamics of refrigerant. Coefficient of performance is given as T1 upon T2 minus 1, and here we will stop.